In this video, we'll see the analysis of Otto cycle and derivation of air standard efficiency for Otto cycle. So let us start with the PV diagram for this. So as shown over here, we have represented the Otto cycle or constant volume cycle on pressure volume diagram. Now the cycle will start from 1 to 2, then 2 to 3, 3 to 4 and 4 to 1. So various processes which are involved are 1 to 2, it is known as the isentropic compression process. The law is PV raised to gamma is equal to constant. Then 2 to 3 is heat supply at constant volume in kilojoule per kg of air. 3 to 4 is the isentropic expansion process according to the law PV raised to gamma is equal to constant, and 4 to 1 is the heat rejection at constant volume process. So you can see that this 1 to 2 and this 3 to 4, both these processes are isentropic process or adiabatic processes, whereas 2 to 3 heat supply and this heat rejection, they are at constant volume. So we can say that V2 and V3 both are same. Similarly, V1 and V4 both are same. As you can see over here, this particular volume is known as the clearance volume, that is VC, and the piston travels from 1 to 2. So 1 to 2 is the compression stroke, so that corresponding volume is known as the stroke volume. So total volume V1, by taking into consideration both these, it will be equal to Vs plus Vc as shown over here. Now let us see the same diagram on TS plane. So as you can see over here, during 1 to 2, which is the isentropic compression process, entropy will remain constant. 2 to 3, the heat is supplied at constant volume, and as the heat is added, we know that entropy is function of heat, and therefore when the heat is added to the system, the entropy of the system will increase. Then 3 to 4, it is the isentropic expansion process during which entropy remains constant, whereas 4 to 1 is the heat rejection process, and during heat rejection, as the heat is rejected, the entropy of the system will decrease, and therefore we'll get this particular line and it will close at this particular point, that is 1. So we'll get this closed cycle 1, 2, 3, 4. Now these are the minimum and maximum temperatures T1 and T3 of this particular cycle. Now before we start with the actual derivation part, let us define certain ratios over here. So compression ratio is defined as volume before compression to the volume after compression. Now we know that volume before compression is V1 and volume after compression is V2. But we also know that V1 is also equal to Vs plus Vc divided by Vc, where Vs is the stroke volume, Vc is the clearance volume. Expansion ratio is defined as the ratio of volume after expansion to the volume before expansion, and volume after expansion is V4 and volume before expansion is V3, but V4 is equal to V1 and V3 is equal to V2. So we can say that in case of Otto cycle, the compression ratio and expansion ratio both are same. Now let us start with the derivation of this air standard efficiency for Otto cycle. So the first process, as we have seen, that we have to consider 1 to 2 isentropic compression process or adiabatic process, during which the law is PV raised to gamma is equal to constant. So applying that particular law to the state points 1, 2, we can say that so the law is PV raised to gamma is equal to constant, that will apply for state points 1 and 2. So we can say that V1 raised to gamma has to be equal to P2 V2 raised to gamma. Now just rearrange the term. So we can say that V1 raised to gamma divided by V2 raised to gamma will be equal to P2 upon P1. Or we can say that V1 upon V2 whole raised to gamma is equal to the pressure ratio P2 by P1. But we know that V1 upon V2 is nothing but what? It is the compression ratio. So we can substitute that value over here. So therefore this will be equal to R raised to gamma is equal to P2 by P1. So where V1 upon V2 is nothing but the compression ratio R. So therefore we can say that P2 upon P1 is equal to R raised to gamma. So this is our first equation that we have seen over here. Now similarly, the relation between temperature and volume in case of isentropic process, we can write down this like that. So it is higher temperature divided by lower temperature is equal to higher volume divided by lower volume raised to gamma minus 1. So therefore we can say that T2 by T1 in this particular case is equal to, again we know that this is compression ratio, so it is R raised to gamma minus 1. So we'll call this as our second equation. Now we'll consider the next process. The next process is what? It is the heat addition process or heat supply at constant volume process. So we know that heat is equal to mass into specific heat into temperature difference. So therefore, in general, we can say that heat supplied is equal to, now in place of mass, we'll substitute M, then specific heat at constant volume, because the process is taking place at constant volume. Higher temperature is T3 and lower temperature is T2. Now we'll assume this mass as 1 kg. So this is in kg, this is kilojoule per kg Kelvin, and temperature difference is in Kelvin. So we can say that if you cancel out this particular term, you'll get heat supplied in kilojoule. But what we'll do, we'll assume this for 1 kg of air. So in place of mass, we'll substitute 1 Cv into T3 minus T2 as it is. So we can say that this can be written in terms of kilojoule per kg. Per kg means for 1 kg of air. So that is our next equation. Similarly, we can apply the gas law over here. So PV upon T is equal to constant. So we can say that P2 V2 upon T2 has to be equal to P3 V3 upon T2, where volume is constant. So we have cancelled out this P, V2 and V3 from both the sides. So we can say that P2 upon T2 will be equal to P3 upon T3. So that is our next equation. Now we'll consider the next process. So next process is 3 to 4 adiabatic or isentropic expansion process. Again, according to the law, PV raised to gamma is equal to constant. So again, apply this particular law to the state points 3 and 4. So we can say that P3 V3 raised to gamma has to be equal to P4 V4 raised to gamma. Just rearrange the terms over here. So P3 upon P4 will be equal to V4 upon V4 raised to gamma divided by V3 raised to gamma. Or we can say that P3 upon P4 is equal to V4 upon V3 whole raised to gamma. Now this is nothing but the expansion ratio. V4 upon V3 is nothing but the expansion ratio. But in this particular case, expansion ratio and compression ratio both are same. So P3 upon P4. So in place of V4 we can write down V1 because V1 and V4 both are same. Similarly, in place of V3 we can write down V2. So V1 is equal to V4 and V3 is equal to V2. So therefore P3 upon P4 can be written as, again we know that this is nothing but the value of compression ratio, that is R. So this is R raised to gamma. So that is our next equation. That is the fifth equation. Similarly, we can use the relation between temperature and volume in case of isentropic process. So higher temperature divided by lower temperature between 3 and 4 is equal to higher volume divided by lower volume raised to gamma minus 1. And again we know that this is the expansion ratio V4 upon V3 and that is equal to compression ratio also. So this is nothing but V1 upon V2 raised to gamma minus 1 and V1 upon V2 is nothing but the compression ratio. So we can say that T3 upon T4 is equal to R raised to gamma minus 1. So that is our next equation. Now we'll go for the last process, that is 4 to 1 heat is rejected at constant volume. Again, as the heat is rejected at constant volume, we can say that it is M into CV into temperature difference. Higher temperature is T4 minus T1. Again we'll assume mass as 1 kg. So we'll get heat rejected in terms of kilojoule per kg of air. So M is 1 into CV into T4 minus T1 kilojoule per kg of air. So that is our next equation. And finally, if required, we can apply again the gas laws over here. That is PV upon T is equal to constant. And again, V1 and V4 we can cancel out, so that we're left with P4 upon T4. P4 upon T4 is equal to P1 upon T1. So now the analysis is complete. So this is our 8th equation. So there are 4 processes and each process is having 2 equations. Now let's see the derivation for air standard efficiency over here. So it is work done divided by heat supplied multiplied by 100. And we know that work done is nothing but heat supplied minus heat rejected divided by heat supplied multiplied by 100. Or we can write down this as 1 minus HR divided by HS, heat rejected divided by heat supplied multiplied by 100. Now substitute the values which we have obtained in the earlier derivation part, earlier analysis part, right? So that we can say that this is 1 minus heat rejection is nothing but CV into T4 minus T1, and heat supplied is nothing but CV into T3 minus T2, bracket complete, multiply by 100. So this CV will get cancelled out from numerator as well as from the denominator. So we are left with the expression which is in terms of temperatures. So it is 1 minus T4 minus T1 divided by T3 minus T2 multiply by 100. Now we'll use the equation, second equation. We'll start with the second equation which is in terms of temperature. So this is T2 by T1 is equal to R raised to gamma minus 1. So we can say that from this we can obtain the value of T2 as T1 into R raised to gamma minus 1. Similarly, from equation 4 Again, that is also in terms of temperature. So from equation 4 we can say that T3 upon, from equation 6, sorry, so it is T3 upon T4 is also equal to R raised to gamma minus 1, which implies that you can find out the value of either T3 or T4 from this. So T3 will be equal to T4 into R raised to gamma minus 1. So these values we can substitute over here in this equation. So our equation which we have written over here, so air standard efficiency will be equal to, in bracket it is 1 minus this numerator as it is, so T4 minus T1. In the denominator, in place of T3 we can substitute T4 R raised to gamma minus 1, the value which just now we have obtained. And in place of T2 it is T1 into R raised to gamma minus 1. So we can take R raised to gamma minus 1 common from the denominator. So we can write down the expression for air standard efficiency in case of Otto cycle as it is 1 minus T4 minus T1. Now take R raised to gamma minus 1 common from this. So in the bracket again we'll have the same term T4 minus T1 that is present in the numerator. So we can cancel out that particular term. So that we'll get a final form of air standard efficiency in case of Otto cycle. So this will be nothing but 1 minus 1 upon R raised to gamma minus 1 multiplied by 100. So this is the expression for air standard efficiency of Otto cycle.